All right, now we're going to talk about momentum in more detail. We're going to learn about how momentum is conserved. I used to work at Fermilab, which is a particle physics accelerator outside of Chicago, and this was like bread and butter in particle physics. You always use conservation momentum. Okay, so up to this point, we've always talked about just one object. You know, like we drop an object, we throw an object, whatever. It's always been one object, you know. And, you know, so for example, if we have a ball, you know, hitting the floor like we just did, we could use impulse momentum theorem to calculate the velocities, to calculate the impulse, which would allow us to calculate the height it rebounds to, all that kind of stuff. Well, now what we want to do is we want to consider both balls. We have two balls colliding. We're not going to just consider one ball. We're going to consider two balls. So let's just pretend that I have two balls, right? So we'll shoot them at each other. And let's pretend we can ignore the friction between the ball and the table. So are there any external horizontal forces on the balls? No. Okay, now, so who cares, right? Well, we'll see. Okay, so right now, I'm going to show you a mathematical proof. Well, physics mathematical proof. And you're going to see it over and over again with conservation laws. So that's why I want to show it to you. Because you'll just see it again, and it's important. All right, we're going to learn a new way of writing F equals ma. That's kind of cool. So, the sum of all external forces equals ma. No kidding, right? Well, that's the same thing as m delta v over delta t. So you're saying, no kidding. And you know, we're going to consider the mass to be constant. So I can put the mass here if I feel like it. I can write it as delta mv over delta t, right? That's okay. Now, what's mv? It's momentum. So I can write this as the change in momentum over the change in t. This is a big deal. You want to remember that. So the sum of the external forces equals the change in momentum over the change in t. I mean, we always say F equals ma, F equals ma, right? But believe it or not, when Isaac Newton came up with this, he didn't say F equals ma. He said F equals dp, or delta p over delta t. So this is really the fundamental equation. So please remember it. Sum of the force equals delta p over delta t. All right. Now, let's consider, let's say we have an isolated system. Isolated system. Well, what's that mean? Well, we've talked about that before. It just means that the sum of the external forces is 0. That's all. Okay. So that means that this is 0. So that's 0, that's 0, that's 0, that's 0, that's 0, that's 0, right? Okay. So if the sum of the external forces is 0, it means that delta p over delta t is 0. Well, if you change something and it's 0, it means it doesn't change, right? It doesn't change. So what does this mean? It just means that the momentum is constant. All right? So that's kind of how you prove a conservation law. If you can say, you know, that the change in whatever over the change in time equals 0, then you can say that whatever equals constant. All right? I mean, honestly, that's how it works. Okay? All right, so what are we saying? We're saying that if you have an isolated system where the sum of the forces is 0, the momentum doesn't change. Another way you can say that the momentum, like before some kind of an interaction, equals the momentum after, right? You know, if it's constant, it doesn't change. So it's constant, all right? It's constant. So there, okay? So for an isolated system, momentum is conserved. So P equals mv is constant. And you can put a sum there if you want to, because you can have more than one particle. So it means P initial equals P final. Now, you have to be careful. Let's drop a ball, or whatever. Let's drop a marker. Now, let's just say the system is the room. is momentum conserved? No! Well, why not? Because the sum of the forces is not equal to 0, right? If the system is just the room, that means that the Earth is exerting a gravitational force on the marker, right, which is not equal to 0, so momentum is not conserved in the y, in this dimension. Okay, all right? So you have to be careful how you define your system. On the other hand, if you define the system as the room and the Earth, then the gravitational force is not external, so the momentum would be conserved. So you just have to be kind of careful, right? Let's say we have two objects moving, like two baseballs or something, whatever. Two baseballs moving horizontally. Bang. So are there any external forces in the horizontal direction? No. But if the room is the system, gravity's pulling down, so we would say that momentum is conserved along the horizontal, but not the vertical. And that's okay, because usually, we just care about one dimension anyway. So that's all right. All I'm saying is you have to be careful. You just got to be careful that you know what exactly you're talking about, what plane or what your system is or whatnot. Okay, so let's get back to collisions. By the way, you're going to have a lab on this. Okay, yeah, so this is a super big deal, right? Momentum is conserved. Super big deal. Okay, so let's say we have isolated systems. And there's two cases that we want to talk about. So here, two billiard balls. So we're going to assume that these are perfect billiard balls. That means when they collide, they don't deform at all. All right? So that's called an elastic collision if the kinetic energy is conserved along with momentum. Okay? So elastic collision. Okay, look at it's isolated, right? So we know that momentum is conserved. But if the kinetic energy is also conserved, if these things don't deform or squish or anything, then it's called an elastic collision. Okay, now let's take the second case. So I wanted to find a picture of rotten grapefruits, but Google Images doesn't have pictures of rotten grapefruits, so whatever. So these are just regular grapefruits. So you can imagine if you collide regular grapefruits, they're going to deform, right? They're going to squish each other, smash each other. And so they're not going to just bounce off each other like this. So for grapefruits, the kinetic energy is not conserved. I mean, look at momentum is still conserved. It's still an isolated system, but kinetic energy is not conserved. So if that's elastic, this is inelastic or non-elastic. So you want to remember that, right? So elastic means kinetic energy is conserved along with momentum. Inelastic, kinetic energy is not conserved, but of course momentum is conserved because we have isolated system. So let's do an example. Here, you read it and I'll erase. Not much to read. All right, so what this means is this is the before, right? Then this is after the collision, okay? That's what it means by then. All right, so here you have these balls both have mass m. This one moves with velocity 1, that one moves with velocity 2. We're going to assume that this velocity is bigger than that velocity, so they're going to collide, and then somehow they're going to stick together, right? Because now the mass is 2m. And it shoots off with velocity v. So we want to use the conservation of momentum to figure out what this v is. Okay? So here we go. All right, so first of all, first question, what is the momentum before? Well, again, remember, momentum is just mv, right? So the total momentum before is just mv1 plus mv2. All right, what's the momentum after? Okay, now the mass is 2m, so it's 2m times v. Okay, now, so you're assuming this is happening along a horizontal plane, no external forces, isolated system, momentum is conserved. Well, if momentum is conserved, we just do it, right? We just say mv1 plus mv2 equals 2mv. So you want to solve for v, so you divide by the m, then you divide by the 2, and that's your answer. And so that's a whole lot less trouble than working kinematic problems, don't you think? So I don't care what this velocity is and this velocity, I don't care what they are. This answer will always be correct, all right? This v, for this situation, where these guys have the same mass and then they stick together, this will always be correct. And it's just due to momentum conservation. So it's pretty nice. Okay, so here's a question. Suppose the entire population of the world gathers in one spot, and at the sounding of a prearranged signal, everybody jumps up. While all the people are in the air, does Earth gain momentum in the opposite direction? So all students, you all pause your video and figure it out and get ready to vote. Okay, we're back. Now think about it. So here's Earth, and you have all the people here, right? Okay, so what's the system? The system is all the people and the Earth, right? That's the system. So are there any external forces that we have to worry about, that we're concerned with? No. So we have an isolated system. Well, everybody's just standing there, right? And so what's the initial momentum? 0. So the initial momentum is 0 because everybody's just standing there. So P initial, which of course is equal to P final, is equal to 0. All right? Wow. It says at the prearranged signal, everybody jumps up. So you can have all the mass of the people times velocity going that way, right? Well, the final momentum has to be 0. So what does the Earth have to do? So the Earth has to go that way, right? The Earth has to move that way to conserve momentum. So there you go. So does Earth gain momentum in the opposite direction? Yes. Earth recoils just like a rifle firing a bullet with a change in momentum equal to an opposite that of the people. So this momentum has to equal this momentum. Just momentum conservation. Okay, now we've been talking about collisions in 1 dimension. In lab, you're going to do collisions in 2 dimensions. So before you have lab, let's do an example so you'll be ready. And what's nice about it, I mean, if you can do a collision in 1 dimension, you can do a collision in 2 dimensions. It just takes a little bit of trigonometry, so it's not a big deal. Oops. All right, so come on, go. So here it is. A billiard ball moving at, so this is along the horizontal plane, okay? So isolated system. So a billiard ball moving at 5 meters per second strikes a stationary ball, same mass. After collision, the original ball moves at a certain velocity at some angle, the other one moves at that angle. That's all. So find the velocity and angle of the ball that was struck. Okay, so this is nothing new. I mean, honestly, all we're going to do is we're going to, so here, if we're looking down, this is what it would look like. So there's stationary ball, here's moving ball, right? So this one moves at some, whatever. So that one hits that one. Then this one goes here. Okay, then, yeah, let's do this. And then the other one goes there, okay? And so, you know, there's going to be theta 1. So all we're going to do is we're going to conserve momentum along this direction, and then we're going to conserve momentum along that direction. So it's a little bit like those force problems that we've done, you know? That's all. It's great. So let's do it. All right, so let's do this one. Okay, let's see. All right, here we go. All right. So yeah, you'll be doing this exact problem, well, not the exact problem, but you'll be doing a similar problem in lab. And I guarantee you there'll be a problem like this on the next exam. And I guarantee you there'll be a problem like this on the final. So there you go. Now this is a nice one because the masses are the same. That's not always going to be the case. So that's the before, and here's the after. Okay, so again, we're looking down, right? This is happening on the horizontal plane. Okay, so that's what's happening. So we just do components, just like with forces. So all right, so momentum is conserved. So Px initial equals Px final. All right. Well, what's Px initial? Well, okay? Look at. We're going to take a shortcut. No units. And the reason I don't want to write units is because I'm going to use an m for the mass, and then I'm going to have an m for the meter, and it's going to get totally confusing. So I'm going to be totally a slacker, no units. So what's initial momentum? It's m times v, right? But v is 5 meters per second. So that means it's going to be 5 meters per second times the mass m. Okay, understand? 5 meters per second times the mass m. mv, momentum. What's the momentum of this guy? 0. Okay. Oh, I forgot to tell you. Whatever. We have to make a coordinate system. So this is going to our x-axis, and that's our y-axis. Okay. So this is our y. That's our x. Okay. What's the x momentum of this guy? Well, it's the mass times velocity in the x direction, right? X direction. So it's going to be 4.35 meters per second cosine of 30. Okay, so that's the x momentum of this guy. What's the x momentum of that guy? So mass, velocity, cosine theta. Okay, maybe make sure you understand that. Now notice we have a mass here and a mass here and a mass here. Well, let's just get rid of them. So we can divide both sides of the equation by the mass. That's a little bit nicer, right? In fact, just get rid of that. There. All right, great. All right, so that was the x. Now let's do the y. So we're on Py initial equals Py final. Well, is there any y momentum here? No. So we have 0, right? Because that's all going to x. There's no y. Okay, here the y momentum is m times velocity, 4.35 meters per second, sine 30. Sine 30. Now we've got to be careful, right? This is going down, so we've got to give it a minus sign. So here the y momentum is minus m v sine theta. Okay, just like before, we can divide both sides by the m. Well, I could have left that. Who really cares? There. Okay, great. And again, if we feel like it, not again, but if we feel like we put that over here, let's do that. So I have v sine theta equals 4.35 sine of 30. All right, so now what are we going to do? Well, now it's up to you. Now we have two equations, two unknowns. You can solve it however you want to solve it. So some people like using substitution. I mean, it's just up to you. Just two equations, two unknowns, like you learn in high school. But let me show you what I think is the fastest way. So let's write this. V sine theta equals 4.35 sine of 30. Okay, now let's divide this side by, let's do a little algebra first. I want to solve for v cosine theta, so I want to pull this on the other side. All right, so pull this on the other side, minus 4.35 cos 30. Yeah? Okay, now let's divide this side by v cos theta. Well, if you do something on the left, you can do it to the right, right? So we divide that by v cos theta. But That won't get you anything. V cos theta is equal to that. Well, let's substitute, you know. So 5 minus 4.35 cos 30. So that's good old, that's good math. We didn't cheat. Now, here's the beauty of it. Here you have a V and a V. What can you do to those V's? Psh, goodbye, right? They divide out. And then what's sine over cosine? It's tangent. So that's tangent. Okay, that's tangent. Okay, but what we need is the angle, right? So therefore, what do you learn in trig? So theta then is equal to inverse tan of that mess. 4.35 sine of 30 all over 5 minus 4.35 cos 30. Okay, so you just plug it in your calculator, you know? Just plug it in your calculator, and I promise you, you get 60 degrees. Okay, now, all right, that's awesome. We got the angle. Now we want to find V. Okay, you can, whatever equation you want. You can use this equation, or you can use this equation. Doesn't really matter, whatever you want. Because you know the angle now. So just, you know, let's do this equation. So let's divide both sides by sine theta, but we know theta is 60, so it's really this. So you just plug it in your calculator, right? 4.35 sine of 30 divided by sine 60. I promise you when you get that, or when you do that, you get 2.5 meters per second. Okay, you better make sure you can do that, because you'll have one like that, I promise you. Lab, exam, final exam. So make sure you can do that. All right. Oh, there's the picture. Wow, what do you know? Okay. All right. This is an awesome question. Suppose rain falls vertically into an open cart rolling along a straight horizontal track with negligible friction. So you're thinking in your head, isolated system. As a result of the accumulating water, the speed of the cart does what? Now, here's a big problem. And I've said this a million times, right? Analyze, don't philosophize. In other words, don't just use your gut feel. Actually do the analysis. Use conservation of momentum. Okay, so students, pause your video and think of the answer, and then we'll come back. Okay, so you have to ask yourself, is momentum conserved? Well, is it conserved along this direction? Certainly not, right? There's forces along the y direction. Is momentum conserved along the horizontal? Yeah, I mean, come on, there was the hint. This was the hint. Horizontal track with negligible friction. So that means mv before the rain hit equals mv after, you know, after. Now, the rain is going vertically. That was the crucial word, another crucial word, right? And so it's filling the cart up with water. So would you agree that this mass is the cart plus the water, right? This is increasing, but momentum is conserved. If the mass is increasing, what has to happen to velocity? If this product is the same, this has to decrease. Horizontal, right? So there you go, okay? So that's kind of a cool question. I hope you understand that. All right, so I used to do particle physics at Fermilab, right, outside Chicago. So I want to give you some examples from particle physics that illustrate momentum conservation. Because like I said earlier, we use it all the time. Okay, so let me explain how Fermilab works. I mean, one of the ways. So this is 4 miles in circumference. So there's magnets inside this, and the magnets, well, okay, so let's just say that the protons go faster and faster. The magnets keep them going in a circle. Then the protons are extracted, and they come out here and they smash into a stationary target. That's one way Fermilab is used. I'll talk about another way in a couple of minutes. Okay, so here's a real, this is real data from a long time ago. Okay, so here you have a stationary proton, right? Here's a stationary proton from the target. Here you have the incoming moving proton, from the accelerator. So the incoming proton smashes the stationary proton, and look at that! All these particles are formed, So this is a neutral particle, which decays into 4 or whatever, right? Okay, so incoming proton smashes stationary proton. All this stuff is formed. All right, so we're going to assume that momentum is conserved. No, it's an isolated system. So therefore, momentum initial has to equal momentum final. And let's do this just because. All right, because there's lots of particles after the collision, right? So we really need a sum because it's the total momentum, total momentum. All right, so let's do the initial. So what's the initial momentum? Well, the stationary target is stationary, so the velocity is 0, so there's no momentum there. So the initial momentum is just the p, the momentum of the proton, right? Just the momentum of the proton, this guy. Okay, now what is the final momentum? Well, it's a mass. It's the momentum of that guy, that guy, that guy, that guy, all of these, right? So what am I going to say? Just the sum. It's just the sum of the momenta, right? So, if you're going to calculate this, let's say that this is the y direction, and so what you do, you'd say like momentum y of the proton equals the sum of the y momentum of all the other particles, right? But then, if you said this is x, what's the initial x momentum? Okay, this is x direction. What's the initial x momentum? 0. So then you'd say, so this is the y, this is the x. You'd say 0 equals the sum of the px particles. Okay, so that's how you do it. All right, now let's get back to Fermilab. So they used to just use it, this is called fixed target, right? So they use the protons to smash into a stationary or fixed target. That's how it was used initially. But then they came up with a better way to do it. Then they came up with whatever. So they have protons going one direction, and then they have something called the antiproton, which is just a negative proton. They have antiprotons going the opposite direction, and they collide, so head on. So that's another way to use the accelerator. So that's called the collider mode, right? It's not the fixed target, it's the collider mode. Okay? Now think about it. If you have a proton, protons coming this way, antiprotons coming that way, same speed, same mass, what's the initial momentum? 0. So what has to be the final momentum? 0. So let me show you some pictures. Okay, so protons are made up of smaller things called quarks. We'll talk about that later in Physics 106. So when you're having protons smashing antiprotons, what you're really having, sorry for the p's, right? P's momentum, P is proton, sorry. So what you're really having, because protons and antiprotons are made of quarks, you're really having quarks smash into antiquarks, okay? And so when that happens, you get a whole bunch of particles being created. But again, same mass, same velocity, so the initial, here I'll do this. So the initial momentum is 0, right? Momentum initial equals 0. So that means that has to be the momentum final, right? Because momentum is conserved. So here's actual data. So this is a whole bunch of particles that way. This is a whole bunch of particles that way. Now again, the momentum, the initial momentum is 0, agree? because they have the same mass and they have the same velocity except opposite direction. So the initial momentum is 0, so the final momentum has to be 0. Doesn't this look like final momentum is 0? I mean, all these guys are going that way, all those guys are going that way, so the final momentum is 0. So that's called a 2-jet event. There's also something called a 3-jet event. Hey, what happened? Oh, there you are. All right. What should it look like? Well, doesn't that look like momentum is conserved? You know, 120 degrees, 120 degrees, 120 degrees, right? And so, okay, so that's real data. So all I'm saying is that momentum is really conserved, all right? Okay, so let's see. Here's a good question for you. So everybody, okay, 2 carts of identical inertial mass are put back to back on a track. Cart A has a spring-loaded piston. Cart B is entirely passive, so no piston. When the piston is released, it pushes against cart B, and what happens? Ignore friction. So everybody pause your video and figure it out. Okay, so we're back. So again, all we care about, there's a track, here's a cart, here's a cart. So one of them has a piston, whatever, who cares, you know? And so, you know, then so you let go. But anyway, before you spring the piston, what's the initial momentum? 0 along the horizontal, right? That's all we're talking about, just horizontal. So Px initial equals 0. So it's isolated, so therefore P final x has to be 0. So what do those carts have to do? Right? They have to do that, just like the 2-jet event, you know? Okay, so both carts gain equal speed, but in opposite directions. And it's only true because of the conservation of momentum. Initial momentum was 0, final momentum is 0. Only way you're going to get final momentum is 0 is if that guy goes that way, that guy goes that way, because they have the same masses. All right, let's see. Oh my goodness, what do you want to do that now? Now let's quit. This is a good place to quit.